Today we're going to start off in the office here because it's warm. Outside it's 3 degrees C. We've got a bit of a cold snap here at the end of November. And for you guys in the States it's about 36 or 37. So yeah, enough to make my coffee go cold very quickly. As I mentioned last time, this session is still something to do with the new Russ Spec machine. But it is a subject all on its own, so I'm going to treat it as such, and then we'll go back and integrate it into the new machine later on in this session when we go out to the workshop. Now, as I rather arrogantly stated last time when we finished the session off, the designers of beam combiners don't really understand what they're working with. Because if they did, they would provide you with all the adjustments that you need to deal with the problem. Now, I'm going to go through in a very scientific and logical way to explain how and why beam combiners work the way they do at the moment and the way they should work. And to do that, I'm afraid I've got to subject you to quite a few of my diagrams. Now, they're not quite so dodgy because I'm sitting here in the office and I've got a ruler and other things to help me. They're not freehand doodles. Now, the whole point of a visible beam, this red beam that we're going to use, is to coexist with the CO2 laser beam, which is invisible, so that you can actually estimate or see where your laser beam is going to hit your work. Now, most lenses are made from this material, this yellow material called zinc selenide, and that allows light to pass through, both red light and the invisible CO2 laser at a different wavelength. Now, different wavelengths have got something called refractive indices, different refractive indexes. Now, what's a refractive index? What is refraction? Well, most of you will actually probably understand what refraction is, even though you might not have done it at school. And that is, if you put a stick into water, it appears to bend. Well, intuitively, you know the stick is not really bent, so there must be something strange going on with the light. And that something strange that's going on with the light is this thing here called refraction. Now, as the frequency of light changes, and we can see that the red light here is at 650 nanometers, and the invisible light that we can't see, our CO2 light, is sitting here at 10,600 nanometers or 10.6 microns. The refractive index changes, and here is a typical graph of the refractive index changes between these two numbers. The reason why I'm pointing this out to you is because the first time that a beam, and we'll just regard this red beam at the moment as being the CO2 laser beam in black, we get, if that beam hits the surface of this lens at say 3 degrees, then it refracts as it goes into the zinc selenide and it changes direction. And it changes direction by 1.25 degrees. It then hits the outer edge of the zinc selenide and pops back into air again. And as it does, it refracts yet again. And the net result is we've got a beam which is coming out of this side of the lens at 3 degrees. When you try and do the same thing with a red diode laser at 650 nanometers, it has a different refractive index, which basically means its stick bending ability is different. So the light comes in and it bends at only 1.13 degrees. Not a lot, I hear you say. No. But it has even less effect when it pops back into air again. Look, we're 2.99 degrees. I mean, this is half of nothing. But when you actually look at this little bit in more detail, as I've done here, what we find is that that beam coming out at 2.99 degrees is actually travelling further to its focal point than the invisible laser beam. So really the point of this exercise is, if you've got a red beam which is slightly off centre, it will still focus exactly the same as this laser beam will focus, but they will not focus to the same point. And so consequently there will always be a small error between the laser beam and the red dot. It could be as much as 0.2. We need to understand a little bit about lenses themselves. Here I've got the same lens, three different conditions. Each one of these blue beams here is the perfect setup for this lens, i.e. it hits the sweet spot on mirror 3 and reflects perfectly down through the axis of the lens. And here we've got the appropriate focal point generated by the beam itself, and I haven't shown the outside parameters of the beam. I've just shown the center line of the beam coming into the lens, but then showing you the focal point after the lens. But what they are showing you is three different conditions for the red diode laser beam. If that laser beam is parallel to the blue beam, i.e. the original laser beam, here's what will happen. It will bounce off the mirror, not at the sweet spot, but it will pass down parallel to the original beam, and then effectively it will become one of the rays that's the normal blue laser beam. It's just another one of those rays, and any ray that passes into this lens is going to be focused. Okay, now look, I've already shown you that it's not going to be focused perfectly on this diagram here, but let's just assume that it will be focused perfectly. Under these conditions, when you get a parallel but offset beam, it's going to be focused at the same point as your laser beam, give or take a little teeny weeny bit. Now, when it sits absolutely spot on with the laser beam, as shown here, again, you've got perfection. So there are two conditions here, one of them perfect, one of them not perfect, but it's not perfect in a rather special way. The beam is parallel to the original laser beam, and you still get the same focal point coincidence between the red and the laser beam. Now things start to get a bit wacky when the laser beam is not parallel to the red dot laser. As you can see here, it's slightly off angle. It hits the mirror, and because it reflects, it'll reflect at a different angle to the laser beam. And as it passes through the lens, it's not passing through the lens at parallel, which is the way the lens is designed to make it focus here. It's passing through the lens at an odd angle, and it will focus substantially further onwards. i.e., look what happens. It is way off where you want it to be. It's going to tell you effectively that your beam is going to land there, whereas in fact it's going to land here, maybe 1, 2, 3 millimeters away. It just depends how big the hole is in the end of your nozzle to allow this light through. Now sadly, the adjustment systems on most beam combiner systems force you almost into this condition here, where it's an almost impossible situation to try and get perfect alignment. Let me explain something very simple to you, the simple concept of how beam combining should work. Oh, before we do that, what I will just go through is this. We talked about the bendy stick effect. Now, when the laser beam hits this so-called window, which is a piece of parallel zinc selenide, it's got the same problem as the lens. It will enter the zinc selenide, it will distort, it'll bend into a different direction, and then it will come out again parallel to the direction at which it came in, because these are two parallel surfaces. You don't get a double you get a double refraction, but the refraction going in is the same as the refraction going out. So what happens is your laser beam comes in here and it does not carry on along this dotted line. In fact, it gets deflected and comes out at a different path to what it goes in. Now that's an important concept that you'll need to remember when we talk about the way in which the red dot combines with this beam, this blue beam, in a few moments' time. Here's our beam combiner. Here's a typical picture of a machine. It hits mirror 1, bounces down to mirror 2, across to mirror 3, and eventually comes down to the work. Now, what I'm really showing you this for is because on my machine, which is a 60/30 machine, this length between here and here, at its fullest extent, the maximum beam length is around about 1.3 meters. This is not the start of the laser beam, because the laser beam gets distorted, and this is where we're going to do our beam combining, just here. So this is the actual start point for the laser beam, and I want you to imagine putting your eye just there with a crosshair that's at this plane. Now 1.3 meters away, we've got another crosshair. You can't see two sets of crosshairs. There's the laser beam, and that's because they're completely axially true to each other. There is no difference between them, whether we're at 0 or at 1.3 meters. That's what you will see. Now, this two coincidental sets of crosshairs is a very vital concept to understanding how laser beam alignment works. This dot, which is the laser beam, will pass through this crosshair perfectly at 0 and at 1.3 meters distance. So here is my 1.3 meter distance, and here's the brick wall that I was talking about, and here's the laser beam passing through that window. But at that point there is where we're going to start talking about our laser beam. Now here we've got something that I'm going to call an intermediate brick wall, and I will show you this on my machine. You cannot accurately describe or set a laser beam coincident with a red dot round X number of mirrors. It's a virtual impossibility. I will explain why in a minute. Now, I'm going to show you what happens if the laser beam travelled in a straight line and did not get bent with mirrors. And that's what this picture shows you. We've got a red dot pointer which is firing at our window, and it's reflecting off that window at the same angle that it hits it. And in this particular instance, sadly, it's flying off at an angle like this. It's becoming a long way off of where we want it to be. This is a very simple ratio of 1 to 10. The first thing I must restate to you is you cannot see this blue beam. You have got no idea where this beam is exiting this window. So you fire the red dot at this window and you look to see how coincident it is with the burn. The burn is there and your laser dot is out here. The starting point, when we started off like this would have been the start point for the red dot, and this would have been the finish point for the red dot. So that's the way in which that red dot would have appeared to your eye looking down the laser beam when you first saw that crude attempt to set the laser beam up. Now, I hope that you can understand this drawing, because this is a very important concept. What we've got to do is to make this red dot line into a dot. I'm a little bit lost for words here, because what that really means is if we want to make that red dot there and ignore all of this, we're going to make that disappear. What that now means that that red dot is now travelling absolutely parallel to our laser beam. Key word there is parallel. Okay, so really, when we tried to set this up here, we shouldn't be trying to set this coincidental here. What we should be trying to do is to make this beam parallel to our laser beam. Look, we might have a chance of succeeding. If we don't make it parallel to the laser beam, we're destined to failure. Ideally, we'd like to make it perfect, so that it absolutely followed the path of the laser beam. Now, as a red dot pointer, it will do a great job. As a means of setting up mirrors, this will be no use to you at all. If you can achieve this, you can use your red beam to set mirrors, because it's a true analogue of the laser beam. This is not a true analogue of the laser beam, but it gives you the correct result, even though there's an error there. Now you've understood the concept of parallelism. If we want absolute coincidence between this beam and this beam, the only way we're going to be able to do that is to have adjustment in the system which allows adjustment in X and adjustment in Y, so that we can change that position to perfectly match that position. And under those circumstances, we've got total coincidence. Now, with the, and please excuse the word when I say crappy systems that are out there, you can achieve this. In other words, you can make it work if you understand how to set the system. But most people don't understand how to set the system and they try and achieve this. And this is not going to work because you're going to finish up with off-angle beams, not parallel beams. Okay, now we're going to go out into the workshop shortly and I'm going to show you how we set the laser beam up using exactly this method. Here is a typical beam combiner. The red dot pointer would normally be sitting in here somewhere. Now, regardless of where it's sitting, this here, where I put that X, is the pivot point. That's the point at which this red beam will move. It moves like this, about this pivot point. And the point that I want to make there is the longer this pivot is, when you make a change to the angle, you'll make a much bigger sweep up and down this window. If I change it a little bit in this direction, just a little bit, look, I've made a huge difference to the sweep position across the window. The first design principle is keep this pivot point as short as you possibly can, because that makes this change of position smaller. So remember, you are looking down the laser beam after this window. Before this window, the laser beam is seeing what we can see in this view here. The window might be 23 millimeters diameter, but by the time it's tipped through at 45 degrees, it's only about 14 millimeters wide. Now, your laser beam is not what the manufacturer tells you. The manufacturer tells you that your laser beam is probably something like 5 millimeters diameter. Okay, that's because it will be specified at something like what they call full width at half maximum. Well, full width is this dimension here on a Gaussian distribution curve at maximum. So half maximum is that. There it is, the halfway point, and it's full width. But look, that's not the width of the beam, that's just a specification. The actual width of the beam, if you allow enough time, that beam will be at least 10 millimeters diameter and maybe even as much as 12 millimeters diameter if you allow enough burn time. You say, oh yeah, but I'm not really allowing much burn time. But you are, because think about cutting a big circle. You've got maximum power for a minute and a half. Well, that's continuous power. There's enough time for this power out here to have a significant effect if it's hitting something in its field. And look, we've only got 11 millimeters of available window to aim at. Can you see what I mean here? Look, there's an occlusion because of this clamp ring that's on here. And that clamp ring, at the moment, it hasn't even got a window in there. So that clamp ring is going to push out even further when we put a window in there, which is 3 millimeters thick. So the chances are that this physical gap for the beam to go through might be as little as 9 millimeters. So you can absolutely guarantee that some of that beam is going to be occluded. Now, this is a very important point, because where do you set this to start with? You know, if you've got a window which looks like this, and then you've got this occlusion at the back here, where are you going to set the laser beam up? Because if you set the laser beam up onto the center line of the window, then it's going to hit here and here. It's going to pass through there, but it's going to hit. So getting the beam through this gap here could be a bit of a problem. Okay, you'd nominally set this up at 90 degrees to the axis of the beam itself. But hey, we've got adjustment here which allows you to rotate it. But what it's really going to do is going to change the angle, because if you change that to, say, down here, maybe 40 as opposed to 45 degrees, this beam will still come in, offset, and go off at an offset position. But the offset position may not be quite as great. This is fixed relative to this, so the beam will still be pointing at the same spot on this face, the other opposite face. So nothing will change there. So that's it, there is no other adjustment there. So this pivoting adjustment only allows us to swing the beam into a parallel position, if you understand what you're doing. Can you swing that beam into a parallel position round a normal machine? I think the answer is probably no. Well, how's our red beam coming in? And look, we're busy reflecting it parallel to the blue beam, bouncing off that mirror on the outside of the beam, and now it's gone inside the beam, and now it's going outside the beam, and this time this is shown in this plane, but of course there's a 90-degree rotation on this, so this line is now either in front or behind this beam. It's not quite where I've shown it here. This is only diagrammatic. So we've got a fairly big 3D conundrum. Well, I'm going to leave you to sort out whether or not you think that you could make that beam parallel down at this point here. I've looked at all these problems and I've come up now with a design. It allows me to set the beam parallel to that beam, and it allows me to move it in X and Y to bring it coincidental to that. I'm just going to step you through the assembly and details of this little unit that I've designed and made. These are the core components for the Mark II beam combiner. Now, it works on a completely different principle to anybody else's beam combiner. In this plastic piece here, I mean, that could be aluminium, but I happen to make it of black Delrin. We have a groove in the front here to take an O-ring. The red LED pointer has to pass through here with the cables first from the front, because it is a snug fit to fit this into that O-ring. So we've got to twist it and wobble it, and it will eventually go in. And as you can see, it is a really snug fit in there. So the LED has got a solid body and an adjustable focus part on the front. You need to push this back until it just sits flush with this housing. Now at the back, you'll see that there's quite a big gap, and the idea of the gap is very simple. Look, we're going to be in a position where we can actually wiggle this around using the O-ring at the front as a pivot. Now we've got two springs here which will only drop into the right holes here. Two springs, two holes. This retaining ring has got two holes in it. Those holes go opposite the springs. So we've got the little tricky operation now of trying to clamp these springs down and get this ring to retain the springs. And there we go, job done. So now you'll see that the springs are pushing this over to one side. So we've had to wobble this around very slightly to get these screw holes to line up. I did identify another problem with this type of red LED pointer, and that is it has a sausage shaped beam. It's extremely difficult to set it up accurately. So what I've done here, I've produced a very, very small 0.8mm hole in the end there, and a fairly big bore in there. And that fits snugly into the end of the LED, so that we've only got a very, very small hole for the light to come out. And that has quite a significant improvement, which we shall test when we put this on the machine. So that is the core. What we've now got to do is get the rest of the assembly built up to give us the other two control elements that we want. One of the elements is in Y and the other element is in X. Well, here is our little beam combiner, the Mark II version, and it's much simpler than the Mark 1 version. You've seen the steering system here allows me to steer the angle of the beam wherever I want, but that doesn't allow me to set the beam in the correct X and Z position, or X and Y position, depending on which way you're looking at it. So this gives me up and down adjustment here, and this little window here, because the beam is aiming at the center of the window initially, we can move this window, so I can move the beam across the axis by adjusting this window, and up and down the axis by moving this. We don't need adjustment across the tube. I know exactly where the burn is relative to the channel that the tube is sitting on, and that height is fixed. So I don't need to adjust this window to put it on beam centerline. It's set on that beam centerline with 2 fixing holes. Now, in addition to those 2 fixing holes, the 2 mountings for these 2 pillars here have got cap-head screws in. And these 2 cap-head screws sit against the front edge of the mirror mount plate. So this whole assembly with these 2 fixing screws is in a fixed position. It's not adjustable. And this is a heat sink for dissipating energy that reflects off the beam on the front face of this mirror, because there will be some. So let's go and fit this onto the machine and see how we set it up. I will just draw your attention to the fact that I've done a further modification to this machine, in that, look, I've had to put this tube down through a slot. So I've had to make a slot in the back here, and in doing so I've also pushed this right against this back face, which is where it originally was planned to be. The reason it was pulled forward was because the beam combiner that they'd used was somehow mounted, let's put it the wrong way round, like that, so that you somehow had to get to the back to make the adjustments, and the tube, there was not enough space, so they pulled this whole tube frame forward. Well, now that I'm turning it the right way round so you can access stuff easily, like this, then hey, we can have this tube pushed back right against the back face here, where it should be. Now, as I mentioned earlier, this tube is in a fixed position on a fixed frame relative to the mirror. So I know where everything is, and it's not going to change. Therefore, I can make this in a fixed position because I know exactly where the beam is coming out relative to this window here. Now, temporarily, I'm not using the LED that Cloudray provided. I've got my own modified LED in there, as I described to you. But the first thing we've got to do before we can start any of this test work is I've got to remove my mirror. Right, so I've moved the number 1 mirror now, and you can see the LED on the end of my machine here. I've had to machine a window in the end of the machine, and I've put a little hinged flap on here. So I'll just tape a piece of card onto there. Right, well, we've got our red dot in here, and we've got our red dot over here, 1.3 metres away. Now, it's not necessarily the crispest red dot over there, but it's got a fairly bright centre. Now I'm just going to give it a quick pulse, and then I'm going to lift the flap, and we're going to make the same straight line pulse over there on the card. So you can see we're absolutely miles out with our red dot. Now if we look at that red dot in relation to that spot, I would say that it's probably about 2 o'clock and maybe 8 or 10 millimetres away from the dot. We'll steer these to try and get that red dot there in the same sort of position. We don't want it on the dot, we want it at about 2 o'clock and 10 millimetres away. About there. That's not far out. So now we come back to here. Well, we've changed this one now to around about 5 millimetres at 12 o'clock. And we'll set that across to 12 o'clock, about there. And 5 millimetres away, let me just go and check. That's closer to 10 millimetres. So we'll drop it down a little bit. And that looks about 5 millimetres. So now we'll check again at this end, and we've changed just a little bit. We're 5mm at about 10:30. So we'll just tweak that so that it goes towards 10:30. About there. After 3 attempts, and you'll never get this in one, it'll always be 3, 4, 5 attempts. You keep zooming in backwards and forwards to try and get coincidence between those two dots. In other words, you want those two dots to be exactly the same position relative to the burn. So now we can assume that we've actually got the red beam parallel to the laser beam. And that took what? 2 or 3 minutes maximum. So now what I've got to do, I've got to raise and lower the beam, which I can do. Look, I can move this beam wherever I want now. So let's put it into the centre of that dot, and now I can adjust this window here backwards and forwards to give me movement in the horizontal direction. Let me just demonstrate for you. Right, so there we go. Look, we've set that right into the centre of our burn. Let's go and have a look to see what we've done on the wall at 1.3 metres away. So it's obviously not quite parallel, because when I look at it at distance, and remember at distance the ratio is 10:1. The fact that the close-up one is on centre and that one is not on centre tells me that we've still got some misalignment. We're not parallel. So we've got to make a final tweak onto here now. Well, I would say that I'm just about spot on now. As I stand here and I've adjusted it, I can get it right into the centre of the burn. So let's have a look what we've done. We've dropped it down to 6 o'clock by about 2mm. So I need to raise this up just a little bit to bring it into centre, and it's just a shade high. So that must mean that again it's not skewed quite correctly, it's not parallel. So I'm going to drop the beam down by just a small amount. Bear in mind, whatever movement I make here is 1/10 back at the short wall. So there we go. Absolutely spot on centre there, and spot on centre there now. So with these adjustments, I've been able to get the laser beam and the red beam absolutely coincident. So I'm just going to lock up the position of the window. In fact, we ought to keep an eye on the distant one to make sure that's not changing, because that's got 10 times as much movement on the distant one. No, that's fine. So we've locked everything up now. Our burn and our red dot perfectly coincide. And yes, we've got perfect coincidence at that end as well. So, success. We've aligned the beam with the red dot. Well, we're just looking at the #1 mirror through the front of the machine, and you can see that it's reasonably well set up, just a little bit high, but it's pretty well central. Let's just see where the burn is. It should perfectly match the dot. Yeah, that's pretty good, as you can see. Just a little bit of lens tissue to take that debris off the mirror. Well, there's the red dot on mirror 2. Pulse. It's looking pretty good. Still reasonable. So the dot's dropped a little bit, so I need to go down just a shade to get better setting. So steer the beam down, which I can do now with the red dot. Now that does make it a little bit easier, because it takes the guesswork out of assessing where the beam is going to hit next. I can see where the beam is going to hit next because it's on the red dot. No, it's not. It's slightly low. So we'll just check that again. Pulse. And pulse. Spot on. isopropyl alcohol, lens tissues, Q-tips. We'll just clean mirror 2 where we've been messing around with it with a bit of card. Just clean it off with a lens tissue. So now we'll do a test on mirror 3. Well, that's reasonable because we're not going to fiddle around too much with that one. It's just got it into the right ballpark. Well, here we are at mirror 3. It looks reasonably well aligned up, but as you can see, we've got as far as mirror 3 now, and the dot and the burn are no longer lined up. I wonder why that is. I mean, we're now out by what, 3 millimeters? Well look, I've just taken mirror 1 off again and we're checking where a red dot is. It's still in exactly the same spot, perfectly lined up with its burn dot. It's give or take a 1/4 millimeter. It's still absolutely where we left it, spot on. I mean, we must be able to trust this. This is a straight line. The laser beam is travelling in a straight line, the red beam pointer is travelling in a straight line, and they line up perfectly. Start bending through mirrors and things start changing. I think this is a perfect demonstration of why I've never trusted beam combiners. Now you've seen absolutely that this beam combiner is fully adjustable. It can set the beam up absolutely perfectly, but the beam and the red dot do not follow each other as it moves around mirrors. After 3 mirrors, it's gone out of position by 3 mil. Okay, now I could tweak the position at mirror 3, but that's not the point. It means it's going to be inaccurate at other places on the table. Okay, now I've had to stop at this point because what I've just seen doesn't make any sense as far as my knowledge of physics is concerned. So here I am in the office doing a little bit of research, and the fact is there is no research to be done. I already know the answer to the question. Everywhere I look with a Google search tells me that light reflects at exactly the opposite angle that it comes in at. What goes in comes out, just as this diagram shows. And there is no change to that law depending on wavelength of light. So the red light and the invisible CO2 light will reflect at exactly the same angles with exactly the same properties. The only difference may be is that depending on the material that we're using here, some light will be absorbed at this interface and not everything will be reflected. Now in the case of our mirrors, it's around about 3% loss per mirror, about. That only affects the output. It doesn't affect the direction of the output. And what you've just seen clearly shows that after 3 mirrors, I've got a 3 millimeter offset between the laser beam and the red beam. When I test it in a straight line, that error is not there. So somehow the mirrors are causing the 2 beams to diverge. I'm going to set mirror 1 so that it fires the laser and the beam out the front of the machine. So we've got 1 mirror only in this equation. So now it's missing the front corner of the machine and it's arriving up here on our piece of card. Let's see where the laser beam is, should we? Well, that's interesting, isn't it? It's roughly what we expected it to be, 3 millimeters away. And that's after just 1 mirror. I'm going to take this mirror out of here, and as you can see, I've marked the back of the mirror with a line. I'm going to turn the mirror, rotate the mirror through 180 degrees. Is that going to make any difference? Technically, no. But we've got to try all these things one step at a time. And it's still on the left by 3 millimeters, so it's nothing to do with the rotation of the mirror itself. And here we have a gold-plated mirror. Absolutely no different. And now a copper mirror. And there we are, 3 millimeters again. So I think we've categorically proved that the material for the mirror has got no effect on it. The rotation of the mirror has got no effect on it. So one has to assume that my beam alignment is out. You can see I've still got perfect beam alignment as far as my target marker is concerned. and let's see what my alignment is like. That's interesting. Now it appears to be 3mm to the right, so maybe my beam alignment is actually not correct, because if that's 3mm to the right, by the time it passes through a mirror it will make it 3mm to the left, which makes sense. So let me just tweak that back into line again. So there we go, that's pretty well lined up. Well, I've got the molybdenum mirror back in again, and let's see what happens now. Well, the answer is we've got near perfection. Not quite, but near. It's a little bit on the low side. Without intentionally wanting to use a pun, let me reflect on this problem for a minute. I'm going to tape a piece of card across the front of mirror 2. That's going to become my first target for setting the beam coincidence. So I've now set that right to the back of the machine, and I should be able to adjust my red dot now so that it's just on the edge, towards the edge. Now if I put a dot on there, so you can just see over the top of this mirror and through this hole here, you can just see the red dot. And if I turn the beam on and off, you can see that the dot and the burn are pretty coincident. So now all I've got to do is to run that out the way and find out where my red dot is. Okay, so now I've got my red dot on a distant wall, and that's pretty well lined up. Just a little tweak vertically, and there we go, spot on. So I've now included the number 1 mirror in the alignment process. So let's go through the beam alignment process again. Target on mirror 2, so look, you can see where the beam is. We've just got to swing that round. Right, that's on target centre there, but that's not important to us. That's just getting the beam approximately into the right ballpark. Our real test will be this one, pulse, and then this is the mirror alignment test. The great thing is we don't have to use the pulse at the moment. Hopefully we can align the red beam to our burn mark. That should be perfect alignment. Not quite, but nearly. So let's do that again with a new target. Remember, this is an iterative process, which means you've got to repeat it several times to get closer and closer and closer to perfection. Now that red dot and beam line up perfectly, as you can see. Yeah, that looks pretty good. As we can see there, the beam is nowhere near the centre of this mirror. Now for most people that might be a bit of a trauma, but for me, all I've got to do is get inside here and loosen off a clamp screw. This channel section is clamped down, and that's what I've just loosened off, this clamp, and one at the other end. All I'm going to do now is to move this whole unit backwards and forwards like this, to move the Y position into the correct place on mirror number 2. So I'm pushing the tube against the back face of the tube enclosure, remember, because that's where I lined it up. So all I've got to do is to slide that along a little bit, and look, I can make that come into the right place. So that was easy enough to put the beam onto the mirror, and that's the basic principle of beam alignment. Always get the beam aligned to the bearing axis to start with, and then as a secondary exercise put the beam onto the centre of the mirror. You cannot do both things at once. They're separate operations. Right, I've just cleaned mirror 2 after we've burnt the target on it, and we'll just check where we are on mirror 3. Now mirror 3 is not going to be very far out. It's approximately right as far as this way and that way is concerned. So let's just do a quick burn on that. Okay, well I think that looks pretty good. Now let's go to the other end, and I'm not really expecting this to be very far out. So the red dot says we're slightly out. So let's make a red dot adjustment before we start. So the red dot says I've got alignment. Let's see whether or not the beam tells me the same thing. Wow! The answer is yes. We've got the x-axis set up absolutely true very quickly. Now that only happened because I was very close to start with. You would normally still have to do that 2 or 3 times, because just because you line it up at this end doesn't mean to say it's still aligned up at the other end. So do not get fooled into thinking that just one hit with your red dot will give you the answer. It won't. So I've just been messing around with that mirror, and I could well have made it a little bit smoky. There's some vapour on there from the card. So I'll just get my lens cleaning tissues out and give that lens a final wipe gently, just to take the film off the surface, because isopropyl alcohol always leaves a film. Well, here's where we got to yesterday, an empty lens tube. And I'm going to pop that empty lens tube into this little fixture that I've made. We'll set up the axes of the laser beam down the centre of this tube. So basically it's setting up the z-axis. And the z-axis will be independent of the flatness or trueness of the table. And now we'll pop our target in the top here, and this is where we got to yesterday. As you can see, our red dot's not too far off the centre, but it's a long way out this way. That's the red dot. What about the beam? Let's check the beam with a pulse. Oh, that's looking pretty good, isn't it? I don't know how this mirror is setting. It could be sitting that way, in which case that's why the pulse is over that way, or it may be actually the wrong height. In other words, we're getting the beam is actually hitting the top of the mirror and coming down here off centre. I don't know what at the moment. So the first thing that we'll do is we'll pop that down into the bottom of the fixture, so those dots more or less line up. Yes, I'm going to bring the beam, the red dot, across very slightly towards the front. And you'll see I've got control of that red dot, look. Okay, by swinging the mirror around. And I'll put it onto the centre of that dot there. Now, there's a pretty good chance, because it was only a fraction out, that I've only got to do that once. As I keep stressing to you throughout this procedure, this is not a once-off setting. If that was anywhere near, say, 2 or 3 millimetres out, I'd have to make an adjustment, and then I'd have to start again. And I'd have to go through that process 2, 3, maybe 4 times to get that degree of compliance between the top and the bottom dot. So we will just test it, just to make sure. And there we go. So I'm extremely happy now with the alignment of this Z. So we can take that fixture away now, and it doesn't matter where we reset this lens tube. We now know that we've set this beam parallel to the axis of the lens tube. As you can see from that cross, it's not coincidental with the lens tube. So the first thing we're going to do is to put the red dot onto the cross, and we do that very simply with this head by just loosening off these 4 screws, and we can raise and lower the head now and see what's happening. Look, as I raise the head, that is one great advantage, I must say, of having the red dot. It tells me what's going on. Just loosen this screw off again. It is possible, look, for this head to move very slightly, but it doesn't matter, because the mirror and this lens tube are all moving together. It's only out of square marginally by parts of a degree with the table. We're not changing the relationship between the mirror and the axis of the lens tube. So let's just snug this up just a little bit and reset it. Now that's the centre in that direction set, but you can see we're slightly out in this direction as well. Now if we want to move it in the other direction, what I've got to do is something else. But up at this end, look, I've got my mirror on a movable slide, so I can set the position across the machine with this setting. That red dot is currently on the centre line with the head as far left as possible. If we've set our x-axis up true, then it's also a cross check to make sure that it's still sitting on centerline when it's at the other end of the axis. Now there's a strange phenomenon that occurs on these machines that many people don't understand, and that is that they've done their calibration like this and everything is perfect, but when they go to the back of the machine, things are not quite as perfect at the back of the machine. That dot has drifted maybe 0.5 millimeter that way and about maybe 1 millimeter towards me. But I guess that what we shall now be able to do, that we've got this red dot pointer, is to get that spot on by adjusting, and this is the trick, mirror 1. Mirror 1 by the merest little hint. Mirror 1 is actually adjusting the y-axis. Now remember, we've just seen that we've proved that the x-axis is absolutely true by watching that spot not move in this direction. If it moves in this direction, it means we've generated a very small problem in the y-axis as we set it up. I need to just tweak the merest hint on the number 1 mirror. And now when I drag it to the front, it is very slightly out. If I run it to this end of the x-axis, you can see that it's still spot on. There's a very slight difference now. I've got to tweak mirror 2 very slightly to get that in line, like that. And now, with a bit of luck, the really fabulous news is that I haven't had to tweak the red dot pointer since we set it on this corner here and projected the red dot out through the machine 1.5 meters or 1.3 meters to a card target. That was how we set the machine up, if you remember, and that's the basis upon which I've been doing all this calibration. So setting the red dot beam absolutely coincident with the laser beam is possible. Then yes, we can set the machine up, not with just the red beam, but with a mixture of the red beam and targets to help us. So we found a practical method for you to use this calibration system here and out the front of the machine. You don't need to modify your machine to set your beam up. That was something I did to prove the system initially. Now the final test will be this. We've got a lens in here. Now I've got this little tool, which is a very quick, simple little tool for anybody to make. Just stick a piece of masking tape behind there. That's the whole point of these 5 dots. We can test it on each corner of the machine, but I don't think we need to. Pulse, and look at that, right through the centre. Okay, so I got a bit carried away with my patterns. Now these patterns have got an outside diameter of 2 millimeters. I've very carefully measured them, and an inside the ink line of 1.6. So we should get a good idea of the positional accuracy as I move around the machine. I've got crosshairs on here because it's going to be very difficult for me to assess exactly where the red dot is. I'm going to have to look at it from 2 directions and set it up on a line. And I ought to just make sure I set the focus right, and we'll see what we get. Pulse. Then we'll do this front corner. Well, you're not going to believe it, but there are actually 5 dots on there. And we're going to have to go and look at them under my 50 times microscope to have a look to see just how good they are. I'm absolutely staggered. I've got to admit that if it's done properly, a beam combiner can produce some fantastic results. I suspect this is probably about the only beam combiner ever built that can produce this sort of accuracy, because we've understood the basic principles behind beam alignment, and despite my wobble in the middle somewhere because of my dodgy beam alignment, and I've left it in so that you can see how sensitive this system is if you're not careful. But if you get it right, these results are actually going to blow you out the water. Here's what it looks like at 50 times magnification. These lines here are 0.2 millimeters wide. Now, if, and it was a difficult task, I managed to get that red dot actually on the centre of these lines, then let's assume that that now is 0.1. It looks as though it's just about 0.1 off of centre. So that's the front right hand corner. This is the back right hand corner, and again looks as though we're around about, that's just over half, so that's about 0.1, maybe 0.12 off centre. The back left, and again I would say that that's 0.1 off centre. Now the front left, again 0.1 off centre, and the middle of the table. Well, I got that one right, didn't I? 0. Now I have to say, I am amazed. I was always hopeful, but never hopeful of anything quite like that. The very, very small dot that I've managed to achieve has allowed me to get precision alignment on the table. Now there are 3 requirements for combining a red diode guide beam into a totally invisible laser beam. These are the 3 requirements that I spoke about at the beginning and proved during the video that they work. Now I've been an advocate for the beam combiner integrated directly into a tube. Now it's not only STP, but other companies as well are starting to manufacture these sorts of beam combiners. Having studied and proved that these are the mechanisms that are required to make a beam combiner, I decided to go back and take a look at how STP and others are actually making their beam combiner. Could I get hold of enough information to establish what they were doing? The thing that made me interested was when I looked at the setup procedure for an STP tube. The only adjustment that they had were 4 screws on the bottom. And all they were really doing, I believe, was swinging the beam into an angular adjustment. They were just setting the beam onto a spot in the distance, which I've demonstrated to you is not the right approach, because an angular beam passing through the lens is going to put you off centre. So here's the basic construction of this style of beam combiner. The laser is firing from this direction. It hits this window and comes out here, and it gets combined with a beam combiner, an LED, which is firing up at the mirror here. So all they're really doing is swinging this beam around. So the beam may hit perfectly on the centre of that window as it enters. It'll then be offset because of refraction when it exits this side. Now there is only one spot, literally one spot, where this LED will meet up with this beam as it exits that window. If you swing this around, you are not going to hit that spot. So there's a pretty fair chance that this is not going to do the wonderful job that at one stage I thought it was going to do, because it's lacking 2 of the key elements required for perfect beam combining. I started off being very cynical and critical of beam alignment. Now I've not changed my opinion in principle because I don't think it's necessary, but having understood how beam alignment works, what all the principles are and what all the strengths and weaknesses are, I think the proof is in this pudding. We've got a beam alignment system that is not difficult to set up and produces fantastically accurate results within 0.1 of where you expect them to be. So on that happy note, I'll say thank you for your time, and I'll see you in the next session where we can carry on testing this new machine.